Hey guys, Angel here, and in the last video we discussed inertia, which is Newton's first law of motion. Now, in this video we're going to discuss Newton's second law of motion, which is formally stated here. Now this is pretty long, but the acceleration of an object that's produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So this is the equation equivalent of what Newton is saying in his second law. We generally know it as F equals ma, and we say that force is directly proportional to acceleration and directly proportional to the mass of an object. And then even though we draw F, we understand that it's referring to the net force. And so that is, in more simple terms, what Newton was trying to tell us. And the reason that he relates acceleration to force and mass is because these are the laws of motion. So he wasn't necessarily trying to relate force, he was trying to relate acceleration because these are the laws of motion. In the last video, we had a scenario with a ball that goes into three different scenarios: one where it's completely at rest, one where it's accelerating down an incline, and the other where it's moving at a constant motion in a frictionless surface. And so now we're going to revisit those scenarios, but we're going to indicate free body diagrams and how those free body diagrams can tell us characteristics about the motion of the object. And so in this first scenario here, with the ball at rest, we've got, if we were to draw a free body diagram, the first thing we're going to do is draw gravity coming straight downwards. Is always the first thing we do. And we're going to call that negative force of gravity, so Fg. And the reason we named it negative is because we're considering downward to be the negative direction, whereas the normal force going directly up is what we consider in the positive direction. Now, that normal force and that gravitational force cancel each other out. Let's just say that one is equal to 10 newtons, and the other is equal to negative 10 newtons. And so our net force, or the difference between the forces, would be equal to 0 newtons. And let's say that the mass of the ball is 1 kilogram. So if our force, our net force, is equal to 0 newtons, what is our acceleration? And very simply, it's the acceleration is equal to 0 meters per second squared. That means that the ball is in no way moving, the ball is in no way increasing in motion. So right now it's at 0 meters per second, and it's going to continue remaining at 0 meters per second or at rest because there's not a large enough force to make it accelerate. And so now we're going to take a look at the second scenario where we know that the ball is indeed accelerating. It's given to us here. And we have that ball at an incline of 45 degrees, and I'm going to already drew out the free body diagram for you here, with gravity again being pointed directly downward. And we're going to call that negative Fg, and that's the same value as the orange ball, because this is the same ball on all three phases, but just different scenarios, different actions going on. And we've got now the normal force at an angle. So the reason we have the normal force at an angle is because of the incline. Normal force isn't pushing directly up on the ball, it's now pushing at this incline. And so what we did was we made an angle of 45 degrees, so essentially we just moved this over 45 degrees. And that's how we got this tilt in our free body diagram. Now what's not shown in the free body diagram is the component of gravity that is making the ball accelerate. The ball is not coming off of the surface, nor is it going into the surface, so that must mean that we have some sort of balance between the normal force and another force here that is not shown in the free body diagram. That other force there is also a component of gravity. So the component of gravity is what's keeping the ball on the surface, and it's also what's causing the ball to accelerate. I'm going to show you how that is. So like we said, it's not going above the surface, nor is it moving into the surface, so that must mean that it's at balance. And we're going to try to draw just about the same size of a normal force, but we're going to call this negative Fgn. And so that's the component of gravity that is keeping that ball on the surface with the normal force. Now, what is causing the ball to accelerate? That's another component of gravity that can be drawn like so to make a right triangle. And so these are the two components of gravity that are causing the ball to accelerate here and then to keep it on the surface. And the reason it's accelerating is because there is no friction force to stop it from accelerating. If we did have friction, and this is a frictionless surface, but if we did have friction and they were equal, then the ball would just remain on the incline. It wouldn't move up or down the incline. It would just remain at rest, or it would be traveling at a constant speed, but we'll talk about constant speed in the next scenario. But in this case, we know that the ball is accelerating because there is a frictionless surface, and so that is where that component of gravity comes from, and we'll call this Fs, S for speed, or what we'll call it, Fa for the acceleration. And so we would actually be able to solve for that acceleration using trigonometry. And since we know that our angle is 45 degrees, then we could do the sine of 45 degrees is equal to the opposite leg, which we called our force acceleration, so Fa, over the force of gravity. And we can actually just substitute in there the acceleration of gravity, which is about negative 10 meters per second squared, but we're going to call it positive since we're dealing with acceleration. And we would just take the sine of 45 and multiply it by 10 meters per second squared and actually get the acceleration of the ball regardless of its mass. So that's just a little tip in there that hopefully will come in handy later in some problems. Now let's take a look at the final scenario that you're going to notice is very similar to the first scenario. In this final scenario, we've got a free body diagram that is identical to the free body diagram of the orange ball. We've got the force of gravity going straight down. We're going to call that negative Fg again. And then we've got the normal force directly upward. So that means that our net force is equal to 0 newtons. And if our net force is equal to 0 newtons, that means we don't have an acceleration. But what's different in this scenario is that we do have a velocity. It went from rest to a velocity after this acceleration, and now it's traveling on that velocity on this frictionless surface, which is why there's no force here. So it's traveling on that velocity on that frictionless surface for eternity. It's in inertia until a force large enough acts upon it to stop it or change its motion. But right now, because it's frictionless and there's nothing pushing on it in any direction, then we don't have a net force. A net force in the vertical direction is 0, and our net force in the horizontal direction is also 0. So this ball is going to continue in its motion for the rest of eternity. It's not going to have any acceleration because there's no net force. So hopefully that was a good little introduction to the Newton's second law. What we're going to move forward with is a problem that we already discussed in the last video, and that was so this should be a very similar scenario. Now I went ahead and just gave you the answers that we got in our last video, and that was that the 50 newtons acting on the box was sufficient to get the box moving because the static friction of the box is equal to 45 newtons. And so 50 newtons is greater than 45 newtons. And then the net force of the box that we solved in the last video was 20 newtons. But the follow-up question here is, what is the acceleration of the box as it is moving? And because we have a net force here, 20 newtons, then all we would need to do is set those 20 newtons equal to our MA, our mass, which is 15 kilograms. And then we're solving for the acceleration. So we would just do 20 newtons divided by 15 kilograms, and that would be 1.33 meters per second squared would be our acceleration. So pretty straightforward. In blue text, I went ahead and added some kinematic questions that you can use for practice, and this is kind of how Newton's laws of motion are going to relate back to the very first things that you learned in this course, and hopefully you can solve the answers for that. I'll go ahead and leave the answers in the description below for you, and just make sure that if you have any questions or any constructive criticism, please leave it in the comment section below. If not, go ahead and give us a like and a subscribe. Thank you guys.